Hello everyone and welcome to SARpy's classification example using deep learning and fine-tuning. In this example, we will be attempting to classify the MPEG-7 dataset using a deep neural network. So first, you're going to need some libraries. Of course, you're going to need SARpy and its requirements such as scikit-learn and NumPy. We recommend pandas and matplotlib for visualization of results. In this example, we will be using both. Now, you're going to need Keras. What is Keras? Keras is an API for neural networks which makes it very user-friendly to develop and train and modify neural networks. It also already comes with the pre-trained weights for a bunch of famous and commonly used neural networks, such as the one we're going to use, Inception v3. Now, what we're going to do with this. After downloading this pre-trained neural network, we will download the weights. We will retrain this neural net with our dataset. This is called fine-tuning. And then we will apply this network to all images in our database. Now, the MPEG-7 shape dataset is available here and also through our library's datasets module. So, first of all, let's set up the workspace. We need to import a bunch of libraries that we'll be using. Let's do this. So, mostly it's NumPy, matplotlib, pandas, nothing very different. And here are the Keras imports. These are a little bit more important. Now, first of all, what we got to do? We need to load the MPEG-7 dataset, and we're going to use SARpy's module datasets.loadmpeg7 function to do this. The Inception v3 model requires all images to be of the same dimensions as one another and have 3 channels. In the original Inception v3, these required dimensions were 299 by 299. We're going to resize all of our images to that exact dimension, and we're going to make them red, green, blue images. So let's load the dataset. We're going to display some load information here just to see if it loaded alright. Now we have loaded the dataset. We can see here the full dataset has 1,400 examples of 70 classes. Now let's just display some of their images and their corresponding class from the dataset, just to visualize what are we working with. Here we have some. So there's the bone, the coma, the glass, the half circle, the heart, a bunch of them actually. Most of these classes have different challenges by themselves. If you look at the dataset, you can see that, for instance, the chicken is always the same chicken shape but rotated, while the children carriage are similar but they are from a real dataset. And the beetle class has several kinds of different beetles in all rotations. So there are a few very interesting challenges in this dataset. Now, we also have to normalize them to the same size. So here we're going to make them 299 by 299 and red, green, blue, 3 channel. Additionally, we're going to convert the target labels, which are 1, 2, 3, up to 7, into one hot lists. So it's a list of zeros and the index of the 1 is the class. Alright, now we're going to split the data into a training and a testing set for the supervised learning process. We're also going to report this information. Note that we convert them to NumPy arrays because that's the input of the Keras model. Okay, so we got 50%. We got 2 halves of the dataset, 700 images in one, 700 images in other. The images are of the proper shape. Now, we are going to retrain the Inception v3 model. How does this happen? First of all, we are going to be loading the base pre-trained model. That's this line over here. And you can see we get the weights from when it was trained with the whole ImageNet data set. Now we're going to replace... Oh, we don't load the top. The top layers are the ones that are responsible for determining classes instead of just extracting features. We don't include it. We're going to replace these top layers with our own. So first we're going to add a pooling layer from the output of this model. It's this line over here. Then we're going to add a fully connected layer with 1024 neurons. This is the layer that I hope we'll learn to predict our classes. We could add more, we could add a different amount of neurons, but we chose to add one dense with 1024. This is based on Kara's documentation example, so it's very similar to what's there, and it works very well, but it can be improved. Finally, we have to add the 70 neuron layer, where each neuron corresponds to a single class probability. So the output of this layer is going to give our classes probabilities. Now we build the model we're going to train with the same inputs as the base model, and the outputs, it's the layers that we just built. And we want to train only the top layers. That's fine-tuning. We are going to freeze every layer in the base model. Of course, you could improve fine-tuning by training some of the top layers in the Inception V3 model. There's a lot of theory behind this, but for now we're just going to freeze them and trust that they extract the proper features. Now we're going to compile our model with the RMS prop optimizer, and loss function is going to be cross entropy. This is practically default, and we're going to fit the model. This will take some time. Alright, so we're back. I'm sure this has been pretty quick for you, but for me it took about an hour. Actually more than an hour. So, now that we have our model trained, let's compute the model's accuracy, average precision, and average recall using the test set. We're going to use scikit-learn's functions for this. So we're going to predict all of the elements in the test set, and then we're going to compare the predicted labels with the true labels. Okay, so we got here, and it's a 57% accuracy, 58 almost. This isn't that great, but again, we just did the basics with this deep learning model. We could like train more layers. We could try other models, simpler models, maybe, since these models were trained on full color images and we're just using them for binary images. And if we had an even larger data set, we could train it from scratch without the previous weights. So these are left for you if you are interested to explore these opportunities. Now let's show the confusion matrix. Here we can see in the diagonal that overall we have some nice results. I mean, there are 20 examples of each class, so I guess 12 and the like isn't that much, but if you are interested in the misses of one particular class, such say crown, you can see where it predicted wrongly. Now finally let's display some of the results so we can judge them by ourselves. So here are some of the results, and we got some pretty interesting results here. You can see that this is a very hard mistake when they say they predict a fly, but it's the device 7, which are these device shapes are a bunch of stars and the like. But you can see that he gets the chicken right despite rotation variance. Same for the horse. The carriage, it also gets right, even though it's from a real data set. He predicts that this key is actually a guitar, which, you know, to be fair, it kind of does look like a guitar. And they get other things right, like these bones, the glass, the flatfish, these device 5, this device 8, the shoe. And he also believes that this turtle is a chicken. Which, well, Not so much, I guess. Anyways, that's it for the example. For further reading, I recommend checking the Keras documentation. And if you are interested or intrigued, just try to retrain the model, train it from scratch, train it with more layers, and try to improve on this result. That's it for this tutorial. See you next time.